So let's take a look at the conformational analysis of ethane. So remember that for any conformational analysis, what you're doing is looking down a particular carbon-carbon bond in the molecule. In ethane, we only have one carbon-carbon bond, so we're going to look down it. So as we saw in the previous video, there's an eclipsed conformation of ethane, and the Newman projection for that looks like what I've drawn above. And there's a staggered conformation of ethane as well. So remember that what we're doing is rotating in 60-degree increments around the bond. So as we do that, we go first from an eclipsed conformation to a staggered, then back to an eclipsed, then to another staggered, then to an eclipsed, and so on as we go around the bond, as we rotate around the bond. Well, if you think about it, and if you practice this with your models, all of the eclipsed conformations look like the drawing shown on the screen right now. And all of the staggered conformations also look like the drawing that's shown on the screen now. So what that means is that all of the eclipsed conformations are identical in energy, and all of the staggered conformations are also identical in energy. So which one of these then is higher in energy? Well, if we think about it, we know that in the eclipsed conformation, in any eclipsed conformation, you're always going to have torsional strain. So an eclipsed conformation always has strain that a staggered conformation does not, meaning that eclipsed conformations are always going to be higher in energy than staggered ones. So in the case of ethane, the eclipsed conformation has torsional strain because the bonding electrons are too close to each other, which is what happens in an eclipsed conformation. The electrons in the bonds align with each other and repel each other. In the staggered conformation, that's not the case. So the staggered conformation has no torsional strain. Now let's go back to the eclipsed conformation. Does it have steric strain? Well, it would have steric strain if any of these pairs of hydrogens were too close to each other. Let's go down to the bottom of the page and look at this little picture in the lower left. So this is ethane shown from the side. So this is very much like the photograph that we saw in the previous video. As it turns out, the length of this carbon-carbon bond, right here, the carbon-carbon bond in ethane, this is long enough, and the hydrogens themselves are small enough that in this region here, between the hydrogens, they can't get too close. Okay, which means that there is no steric strain in eclipsed ethane. So the hydrogens are small enough and the carbon-carbon bond is long enough that it can keep them apart from each other. So there's no repulsion and therefore no steric strain. Now let's go back up to the top and add that piece of information in. So we have torsional strain in the eclipsed conformation, but no steric strain. Now, it should be noted that as soon as you get a group that's larger than a hydrogen on there, so let's say that we had a hydrogen here, color this in. So let's say that this blue dot is still a hydrogen, but on the back bond, let's say that that pink dot is now a methyl group. Well, now, as we saw in the photograph in the first video, when we talked about steric strain, now those are close enough. So the hydrogens on a methyl group are going to be close enough to the blue hydrogen that you would get some steric strain. So as soon as you have groups that are larger than hydrogens, even just one of them, even in an eclipsed conformation, steric strain can occur. In the staggered conformation, though, by contrast, now those hydrogens are even farther apart from one another, so there's not torsional strain, nor is there steric strain. So the staggered conformation has zero strain energy, and the eclipsed conformation we're going to see. So what we've decided is that because the eclipsed conformation has strain that the staggered conformation does not have, it's going to be higher in energy. So we're going to start by plotting an eclipsed conformation right here. So the energy of that is 3 kilocalories per mole, and we'll talk about that in just a few minutes. First of all, notice what we're doing here as we plot this. We're plotting the strain energy in kilocalories per mole on the y-axis versus the dihedral angle or the torsion angle on the x-axis. And so again, remember that we rotate around the bond in 60-degree increments. So these tick marks are all 60-degree increments. And notice also that you're always going to start your conformational analysis around any bond with an eclipsed conformation. So you have to start it at a 0-degree torsion angle between the two bonds that you're looking at. So always start with an eclipsed conformation. Okay, so we start with the eclipsed conformation, and I've just drawn the energy level of that in. So it's 3 kilocalories per mole. And then we're going to go, after a 60-degree rotation, to a staggered conformation, and then back to another eclipsed, and then to a staggered, and to an eclipsed, and a staggered, and then finally another eclipsed. Once you've plotted all of the energy levels of the different conformations, then what you can do is draw a smooth curve connecting all these points. Like so. Now for any set of conformations around a particular carbon-carbon bond, we should note that all the conformations are in equilibrium with each other. So all of these conformations are in equilibrium. And then as it says here, the most stable conformations are the most populated. That means that most of the molecules in an assembly of molecules, in your collection of ethane molecules in this case, are going to be in the staggered conformations because those are lower in energy. So we would say here, more molecules at any given point in time exist in the more stable conformations. So I just told you that the conformations are all in equilibrium with each other. So how does one conformation turn into another conformation? Well, we just saw this when we worked with the models. The bond is rotating, but what's causing the bond to rotate? What causes the bond to rotate, remember, is the input of energy. So where is this energy coming from? It comes from collisions. So what happens is that a high energy conformation, for example, an eclipse conformation, like this guy up here, can slam into a low energy conformation, and in doing so, it transfers its energy from itself to that lower energy conformation. When it sheds that energy, it goes down to a lower energy conformation, and the low energy conformation that picked up that energy now is in a higher energy state. So energy is transferred among the different conformers or conformations through collisions. We can also, at this point, revisit what we saw in the first part of the notes, and that is the barrier to rotation, or the rotational energy barrier. So let's give this a more precise definition. This is going to be the difference in energy between the highest energy conformation around a particular bond so the highest energy conformer and the lowest energy conformer, again, around a particular bond. So in the present case, for the carbon-carbon bond in ethane, the barrier to rotation is 3 kilocalories per mole. We're getting that from the fact that the eclipse conformation, any of the eclipsed conformations, have energies of 3 kilocalories per mole, so strain energy of 3 kilocalories per mole, whereas all the staggered conformations have no strain energy. So their strain energy is 0. So the difference between the two is 3 kilocalories per mole. Now, how much energy is that? Okay, so let me give you a couple of other numbers to put this into context. So at room temperature, for an assembly of molecules, we estimate that there's about 20 kilocalories per mole of energy available. In other words, at room temperature, there's plenty of energy to an assembly that's available to an assembly of ethane molecules that bond is going to be rotating constantly. Okay, so there's a ready supply of energy to cause that bond to rotate. To put this in a different context, a typical carbon-carbon single bond, so now we're not talking about a rotational barrier, we're talking about a bond energy or a bond enthalpy. The bond enthalpy here is along the lines of 90 to 100 kilocalories per mole. That's the amount of energy that you would have to put in to break the bond. So as you can see, that's a lot more energy than is required to rotate around the bond. Let's push on this idea of the 3 kilocalories per mole. And to do so, let's go back up to the picture of eclipsed ethane. So I'm going to get rid of all this highlighting so that we can talk about what's going on. So the eclipsed ethane has an energy, again, of 3 kilocalories per mole. That's attributable to the sources of strain that are present within that conformation, which we assessed earlier has only torsional strain. So you have an area of torsional strain here because these two carbon-hydrogen bonds are eclipsing one another. You have another area of torsional strain here because these two carbon-hydrogen bonds are eclipsing each other. And finally, you have a third area right here with the final pair of carbon-hydrogen bonds eclipsing one another. So if we apportion that 3 kilocalories per mole, what we can see is that the contribution of each of those pairs of eclipsing bonds must be 1 kilocalorie per mole. So let's go down here and write something out about that. We can say that the energy cost of what we could call, as a shorthand, a hydrogen-hydrogen eclipse is 1 kilocalorie per mole. So for each HH eclipse that you have in a particular conformation, it's going to cost you 1 kilocalorie per mole of strain energy. Now, HH eclipse means a pair of eclipsing carbon-hydrogen bonds. The carbon on the front, or the front carbon rather, and its bond to hydrogen eclipsing the bond of the back carbon with its hydrogen. So a pair of eclipsing carbon-hydrogen bonds. So these are the principles that we're going to use to do any conformational analysis at all. So let's look at some other things about drawing molecules first, and then we'll do a slightly more complicated conformational analysis. Okay, so we need to have some different ways of drawing organic molecules. And so we're going to start expanding that idea now. So we're going to talk about 3 ideas. The first one is the Newman projection, which we've been looking at in the context of this packet of notes. So these photographs are not the best, but I'm going to interpret them for you so that we know that we're all on the same page. So the bonds in the photograph, the bonds in the front, which I'm going to make more obvious, so the bonds that I'm coloring in with these bold lines are black, so that's the front carbon. And notice that at the very top, there's a methyl group that's composed of yellow hydrogens. So that's a CH3. And I'm going to color it in yellow because those hydrogens are yellow. Also on the front carbon, we have this hydrogen, which is blue. So I'm going to say HB is over here. We have this hydrogen over here that is red. So that guy goes over here. And now we can focus in on the back carbon. Now it's a little bit hard to see, but the 3 bonds coming off of the back carbon, remember the bond between the front carbon and the back carbon is invisible to us in the Newman projection. The bonds coming off of the back carbon are red sticks in the model that I constructed. So here is an orange hydrogen. So that's on the back carbon. So it's going to be this bond right here. And then on the other side is a green hydrogen. So that's going to be this guy right over here. And then pointing straight down, stemming from the back carbon, this guy here is a methyl group, and those are blue hydrogens. So I'm going to put methyl. And color that one in blue. All right, so we have yellow methyl that's attached to the front carbon. Let's put a dot on the front carbon, which is attached to the back carbon through a bond that we can't see in the Newman projection. So the back carbon is the circle, and to the back carbon is attached another methyl group. So we have a 4-carbon chain, so this molecule is butane. Now if we take the model and we rotate it, so we're going to just tilt it so that we're no longer looking down that central carbon-carbon bond. Okay, so let's draw a little picture of butane over here. So 1, 2, 3, and 4. So the Newman projection that we're looking at is looking down C2, C3. So C2 is the front carbon and C3 is the back carbon, which makes the yellow methyl 1 and the blue methyl carbon 4 in the chain. So if we take this and we rotate it 45 degrees, now you're able to see the carbon-carbon bond between carbons 2 and 3. So carbons 2 and 3 are here and here. And so now let's track with what we have going on. So the yellow methyl group is still carbon 1 and it's still pointing straight up from carbon 2. So here's our yellow methyl group. And similarly, on the back carbon, which was 3, the blue methyl group, or carbon 4, was pointing straight down. Now let's fill in the other atoms. So referring to the structure, notice that here's the red hydrogen. So that's going to be over here on the right. Here's the blue hydrogen. That's going to be on the left. Notice that those were the 2 hydrogens attached to carbon 2 in the original Newman projection. And then on the back carbon, we have the orange hydrogen and the green. So on carbon 3, we would draw HO and Hg. If we do another 45-degree rotation, so 45 degrees from the sawhorse projection, then what we get is the following. This is called a perspective drawing or a wedge and dash notation. A wedge and dash notation method of drawing the molecule. So in this instance, what we see is that the bonds in the carbon backbone of the molecule are drawn in the plane. Okay, so when a line is drawn just like a regular line, that means it's in the plane of the paper. This is carbon 1, here's carbon 2, here's carbon 3, and here's 4. We know that carbon 1 is the yellow methyl group. We know that carbon 4 is the blue methyl group. And so now what remains to be done is to look at what's on the other carbons, 2 and 3. So referring to the photograph, what we can see is that the red hydrogen is pointing out towards us. So the carbon-carbon bond or the carbon backbone, I should say, is what I've just highlighted in green. So here's carbon 1, 2, 3, and 4. So at carbon 2, the red hydrogen is coming forward. So we're going to draw the bond to it coming from carbon 2 as the wedge. So a wedge means forward. And going back is the blue hydrogen. So the bond to it we depict with the dash. So a dash means going back behind the plane. So a dash is going behind the plane, and a wedge is coming forward out of the plane and toward the viewer. What's coming forward at carbon 3? Well, it looks like it's this green hydrogen, and it looks like the orange hydrogen is pointing back. So we'll put HO on the back bond and HG on the forward bond. So you should repeat this exercise with your own models and work through it. You can use a blank copy of this and just work through the exercise, changing the orientation, changing your viewpoint of each structure so that you can track and go from a Newman projection to a wedge and dash notation. Typically, one of the easy ways to do that when you're starting out is to go through the sawhorse, but you don't always have to do that. Okay, let's apply what we know to the conformational analysis of butane. So we're going to continue our discussion of butane. Oop, not yet. I skipped. So let's look at this. Okay, so how would you draw a Newman projection from a skeletal formula? So first of all, let's draw a skeletal formula. And I'm just going to make this general. Like so. So remember, you're always looking down a particular carbon-carbon bond in the molecule, and that'll be specified in the problem that you're given. It'll say, do a conformational analysis around the C2, C3 bond and blah, 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 name of molecule. So let's do that here. Okay, so we're not going to do the full conformational analysis, but we are going to look down a particular bond, and let's look down this bond that I've highlighted in green. Okay, so if you're doing that, what that means is that you're going to be standing on one side or the other of that bond. So you could either stand over here and look down the bond that way. So here's you. Or you could also stand on the other side of the bond and look down it that way. There's you again. It doesn't matter which side of the bond you stand on, because you're going to get the same relationships between the groups on the two carbons involved in the bond as you rotate around the bond. So that's really up to you. It doesn't matter which side you look down the bond from. Let's draw a Newman projection, though, from the point of view of this. Okay, so we'll get rid of the other one. And so let's draw the Newman projection. So first of all, we'll draw a circle. The point in the middle of the circle is going to represent the front carbon. Okay, I'm just going to number these carbons 1 and 2. So this will be 1 and the circle will be 2. So what you need to do here is imagine yourself, at this point you're looking at the molecule, but you're on the side of it. You can see the bond that we're going to be looking down. So you need to put yourself in the plane of the paper on the left side of the molecule and imagine what you would see if you're looking down that bond and carbon 1 is directly in front of you. What you would see is that directly in front of you and pointing straight down is the bond to C, whatever that is. Remember, you're now in the plane of the paper and looking towards the right side of the screen. So that means that B is extending to your right, like so, which leaves A as extending to your left. A is going behind the page, you're in the plane of the page, so it will be to your left based on your perspective toward that bond. On the back carbon, what we see is that F is pointing straight up, E is to the right, and D is to the left. So this is an example of a staggered conformation. Let's try another one so that we can see an eclipsed conformation. Okay, so let's put some labels on here. We'll call this J, K, L, M, N. We'll call that one P. We'll skip O. Okay, so again, we're going to look down this bond here, and I'm just going to call this carbon 1 and this carbon 2. So to look down the bond, you have to imagine yourself standing in the plane. So you're in the plane of the paper now, and you're looking down that bond. And what you would see is the following. Here's carbon 1. The circle is carbon 2. Pointing straight down in front of you is J. What's pointing up and to your right? Remember, you're in the plane of the paper now, looking towards the right side of the screen. If you said L, you are correct, which means that K is going to your left and pointing up. On the back carbon, it's P. The bond to P is pointing straight down. The bond to N is toward your right, and the bond to M is going to be behind K. Okay, now let me change one thing here. There we go. Okay, when you draw these, people always ask, which side of the front bond should I put the back bond on? Okay, so let's use the PJ example. Okay, so here's the bond to J, and so what people want to know is, do I put the bond to P over here, or can I put it over here? Okay, now I started by putting it on the right side, but then on the other two, I put those different. So you want to do it in the same way through the whole Newman projection. So if I have this if I have the bond to P, slightly to this side of the bond to J, then I'm going to do that over here and over here as well. So it's not a big deal, but if you want to be consistent, then it looks nicer to do it that way. Okay, so those are two examples of how you would take a skeletal formula that's drawn with wedge and dash notation and convert that to a Newman projection. Okay, we'll have other examples where we're going to be able to go back in the other direction, but you could start working on those now if you wanted to do that. For now, let's turn our attention back to the conformational analysis of butane that was promised a few minutes ago. So let's take a look at what we have. Okay, so for this, it might help to make a model, because what we're going to do is fill out a set of Newman projections, and then we're going to fill in some energies and calculate a rotational barrier. So let me give you a little bit of information to start out with. First of all, CH3, as you know, is an abbreviation for methyl. But you can also just write, as you may also remember from the first nomenclature packet, Me. So that takes up a little less room, so that's probably what we'll use for our notation here. We're also going to be assessing energy values, and so let's just say up here, so that we don't have to write the units everywhere, that our energy values are going to be expressed in kilocalories per mole. So that'll be true for all of them. Okay, I'm going to get you started on the first one. And remember, the first one has to be an eclipse conformation. And we see that reflected right here. So the eclipse conformation that I'm going to start out with, remember we're looking down C2, C3. So here's 2, the circle is 3. I'm going to draw out the highest energy eclipse conformation. That's going to be the one where the 2 methyl groups are eclipsing one another. So when we fill in all the other atoms, we get a structure that looks like this. So the methyl group that's that's bonded to carbon 2 and pointing straight up, that's carbon 1. The front carbon is carbon 2, the back carbon is carbon 3, and the methyl coming off of carbon 3 in the back carbon is carbon 4. Okay, so that's our starting point. So what I'd like you to do is to pause the video and fill in the other ones. And so what we're going to do is the following. So that we all have the same drawings at the end of this, we're going to keep the groups on the front carbon in exactly the same positions. So we're not going to move those, but we're going to rotate the back groups, and we'll do so in a clockwise fashion. So let me do the first one for you. So if we rotate in a 60-degree increment, remember these are all 60-degree increments, if we rotate 60 degrees around the bond in a clockwise perspective, or a clockwise fashion from our perspective, that's going to put the methyl group that's carbon 4 over here. So this is 4. Here's 1, 2, and 3. And it's going to shift those 2 hydrogens over as well. So continue that and draw all of the other conformations, keeping the front groups in position and just rotating around until you do a full rotation around the bond. Once you've completed that, then unpause the video and we will continue. And voila, there they are. So now let's assess the energies of each of these individual conformations or conformers. So we know already that a hydrogen-hydrogen eclipse carries an energy, a strain energy, of 1 kilocalorie per mole. So let's put those numbers in everywhere we see a hydrogen-hydrogen eclipse. So in structure A, and I'm referring to this label up at the upper left corner of the box, in structure A we have 2 such eclipses. In structure B we don't, because that's a staggered conformation. In structure C we have 1. And that's this guy right here. So that's 1 kilocalorie per mole. Structure D, again, that's staggered conformation, so we have no eclipsing interactions. In structure E, there's 1 hydrogen-hydrogen eclipse, so that's 1 kilocalorie per mole. And then finally in structure F, again, it's staggered, so there are no eclipsing interactions. So now what other types of interactions do we need to look for? Well, let's go back to structure A. So we put in the energies of the HH eclipses, but what about the methyl-methyl eclipse? Do you think that's going to be a higher energy? Will that cause more strain or less strain than a hydrogen-hydrogen eclipse? So if you're thinking that it causes more strain, you're correct. And the energy value associated with this is 4 kilocalories per mole. So that gives us a total for this conformation of 6 kilocalories per mole. So that's its strain energy. Okay, so let's see if we can find some other eclipsing interactions. Okay, we'll skip over B because that's staggered, but we're going to come back to that. Let's look at structure C. So C. Okay, so we have a hydrogen-hydrogen eclipse, which we've already labeled with its energy, and then we have a pair of methyl hydrogen eclipses. Those are also going to have some strain energy associated with them, which is going to be slightly larger than the HH eclipse. Because again, since one of the groups is larger than a hydrogen, you not only have torsional strain because the bonds are eclipsing, but you also are going to have a little bit of steric strain. Each of those carries a strain energy of 1.3 kilocalories per mole. So when we total the energy, the strain energy for that conformation, we get 3.6. Let's go down to structure E, where we have pretty much the same situation. We have 2 methyl hydrogen eclipses, each with an energy cost of 1.3. So that's going to give us a total strain energy for this conformation of 3.6. Now let's go back to structure B. Structure B is a staggered conformation, so it has no torsional strain. However, that's not to say that it will lack steric strain. So as it turns out, these two methyl groups are a little bit too close to each other, and the hydrogens that are stemming from these methyl groups can get close enough to one another to repel. So there's a little bit of steric strain that's present in this conformation. That amount of energy is 0.8 kilocalories per mole. So because that's the only source of strain present in that conformation, that would be the total strain energy of the conformation. We also see this same pattern show up in the conformation that we've labeled F. So the methyl groups are a little too close. Even though it's a staggered conformation, the hydrogens coming off of the carbons on each of those methyl groups can get too close to one another, and so that's another 0.8 energy cost. We're going to look at a more detailed picture of this in just a few minutes. Okay, so that's also 0.8 as the total energy for that conformation. Now let's finish up with structure D. When you have two methyl groups that are gauche to one another, as we do in conformations B and F, that has a name. That's referred to as a gauche-butane interaction. If it's anything smaller, if either one of those groups is anything smaller than a methyl group, though, you're not going to have the steric strain. So a gauche-butane interaction, let's add this in, is an example of steric strain. The hydrogens on the methyl groups are too close. They repel each other. That's not the case in structure D. So in structure D, if we look at this methyl group and this hydrogen, they are in a gauche relationship with one another, but they're not close enough to cause a gauche-butane interaction. So that's going to be true all the way around this conformation. We don't have any steric strain at all. So we would say that the energy, the strain energy associated with this conformation would just be 0. So now let's plot all of these conformations on an energy diagram. So conformation A has an energy of 6 kilocalories per mole. Conformation B is 0.8. C is 3.6. D is 0. Notice that D is the conformation where the methyl groups are anti to one another. E is also 3.6. F is 0.8. And then continuing the rotation takes us back to A. So then connecting all the points with a smooth curve, we get this diagram. Now let's go ahead and calculate the barrier to rotation around the C2-C3 bond in butane. So remember that the barrier to rotation is the highest energy conformation, whatever its energy is, which in this case is 6 kilocalories per mole, minus the lowest energy conformation, which in this case is D, which has a strain energy of 0. So 6 minus 0, so the barrier to rotation is 6 kcals per mole around the C2-C3 bond in butane. Okay, let's take a look at one more thing, or a couple of more things, and that is torsional and steric strain in butane. And so we're going to reference the conformational analysis that we just finished. So the first thing, we started with the eclipsed conformation. Now we started with the highest energy. So instead of saying fully, not the fully eclipsed conformation, let's say in the highest energy eclipsed conformation, and this is looking down C2, C3. So the highest energy conformation is the one where the C1 and C4 methyl groups eclipse one another. In that conformation, we have both torsional strain and steric strain. Now this is a little bit easier to see if you look at the molecule from the side, as shown in the photograph on the right. When you look at the molecule from the side, what you see right here is that that's where the hydrogens on the methyl groups are too close to one another, and they're very close. So there's a considerable amount of steric strain going on here. But the bonds are also aligned because it's an eclipse conformation. So that would be these bonds here, and of course all of the other bonds on the front carbon eclipsing the bonds on the back carbon. So you have both torsional strain because those bonds are aligned and eclipsing one another, but you also have steric strain because these hydrogens are too close to one another. So in the highest energy eclipse conformation, there's both torsional strain and steric strain. Now let's think about the staggered conformations. So the staggered conformation on the left corresponds to conformations B and F from the previous page. So both of them have the same energy. This one is B, but F is going to have a very similar picture. It's just that the methyl group on the back carbon will be on the left side instead of the right side. So in this case, it's the hydrogens coming off of the methyl groups on the first carbon and the fourth carbon that are too close to one another. That causes the repulsion, which results in steric strain. Steric strain raises the energy of the conformation. We would call this a Gauche-butane interaction. And the term interaction here implies strain. By contrast, if we look at a different staggered conformation from our conformational analysis on the previous page, look at this methyl group here and this hydrogen. So based on where the bonds are, it's this bond and this bond. Those bonds are gauche. So there's a gauche relationship between carbon 1 and that hydrogen, but no steric strain. So that hydrogen that I circled by itself is too small to get into trouble with the hydrogens on the methyl group at C1. So a Gauche-butane interaction, let's give a little more of a definition to that. A Gauche-butane interaction is something that you can find in a lot of different molecules. It doesn't just happen in butane, but butane is the simplest molecule where it happens, and so we name this particular interaction after butane. A Gauche-butane interaction involves a 4-carbon pattern, just like you see in butane, where the first and the fourth carbons are gauche to each other. So a 4-carbon pattern where the first and the fourth carbon in the pattern are gauche. The hydrogens on those carbons are too close. And this is what causes steric strain. I strongly encourage you to make a model of this so that you can see what it is that I'm talking about. And the most effective way to do it is to make the bonds to all the hydrogens so that you can really see what's going on. Okay, so let's look at 2 examples of this that are not butane. Okay, so we have this molecule. So let's just say, let's see if we can figure out what this is. Let's say that this is carbon 1, here's carbon 2, the back is carbon 3, we'll call this carbon 4. So we have a 4-carbon chain. And then it looks like there's an additional methyl group, which would be this guy over here, that's sprouting off the back carbon, which is the third one. So our molecule would look like this. And once we look at it that way, we can see that the numbering that I've applied to it doesn't necessarily track, or it doesn't track at all with IUPAC numbering. We would have numbered it in the opposite direction, but that's okay. We just needed, for this exercise, some points of reference. Okay, so a gauche-butene interaction is a 4-carbon pattern where the first and the fourth carbons are gauche. So let me get rid of these numbers so that we can draw in some new numbers. Actually, I didn't need to get rid of those. Put them back in. 2, 3, and 4. Okay, so our first pattern involves carbon 1. So 1, 2, 3, 4. So it's a 4-carbon pattern where the first carbon and the fourth carbon are gauche to one another. So there's a gauche-butane interaction right here. Now, a lot of the time, to represent steric strain, people will draw these little, they look like kind of collapsed parentheses. So that's the symbol for steric strain, and you see that up above as well. But you also have the same thing going on the left side. So if we number again, here's the first carbon, say the back one is second, front carbon is 3, and this guy here is the fourth carbon. So the fourth carbon and the first carbon are gauche to one another, and so you have a gauche-butane interaction in that region as well.